Begin by introducing some general terms that are needed to discuss differential equations in this course. These terms will be used throughout the semester, so you will need to be familiar with them. All of this information can be found in Chapter 1 of your book. We start by introducing a differential equation. A differential equation is an equation that relates an unknown function with its derivatives. The solution of a differential equation is a function, as opposed to an algebraic equation where the solution is a number. We now look at two examples. First, we see an unknown function y of t as being related to its first derivative. This is a differential equation. Next, we see the derivatives of an unknown function u being related to it. Note that u depends on both x and t, and partial derivatives are needed to discuss the second example. This leads very nicely to the definition of an ordinary differential equation and a partial differential equation. An ordinary differential equation, or ODE, is one where the unknown solution depends on one variable only, and thus ordinary derivatives are used. In a partial differential equation, or PDE, the unknown function depends on more than one variable, and so partial derivatives are used. Looking at the first example, we assume that u depends only on t because ordinary derivatives are used with respect to t. Note that the a, b, and c are known constants, and f of t is a known function. In the next example, we know that u depends on both x and y because partial derivatives are used to express the differential equation. The order of a differential equation is the order of the highest derivative appearing in that equation. So this ODE has order 1, since the highest order derivative is 1. While this PDE has order 2, since it has a second order derivative. Most differential equations that model the physical world are either first or second order. A differential equation is linear if each term contains at most one factor of the unknown function or its derivatives. Also, the unknown function and its derivatives are not arguments to a nonlinear function such as sine, cosine, or tangent. A differential equation that is not linear is called nonlinear. Let's look at two examples of a nonlinear equation. First, we see an equation that is nonlinear because the unknown function and its derivatives are multiplied together. The first term contains two factors, not just one, that has the function or its derivatives, so it's considered nonlinear. The second example is more obviously nonlinear, since the derivative and the function are inputs to a nonlinear function. On the left-hand side of the equation, we see that the derivative of u is being cubed, while on the right-hand side, we see that u is an input to the natural log function. Neither of these functions, the cubed function or the natural log function, are linear. The final example is linear because each term has only one factor of the function or its derivatives in it, and none of the terms have the function or its derivatives as inputs to a nonlinear function. Note that the independent variable is nonlinear, and this is fine. It is still a linear differential equation. When discussing linear differential equations, we only care that the unknown function and its derivatives are linear in the equation, not that the independent variable needs to be linear. Therefore, the fact that y is being raised to the fourth power and x and y are inside of sine and cosine functions does not make the differential equation nonlinear. A linear equation is called homogeneous if the zero function is a solution to the equation. Otherwise, the equation is called inhomogeneous. As an example, note that u equals 0 is a solution of this differential equation, du dt equals 3u. However, if we change the ODE by adding a term, we see that u equals 0 is no longer a solution. If we were to plug in the 0 function for u into this second ODE, we see that the left and right-hand sides would not be equal to each other. Homogeneous linear differential equations have a very important property that we will utilize often in this course. If the functions u and v are solutions of a linear differential equation, then a separate function w, which is alpha u plus beta v, is also a solution, where alpha and beta are real numbers. Therefore, if we take some linear combination of two known solutions of a linear homogeneous equation, that linear combination is also a solution. To demonstrate this, let's consider the ODE du dt is equal to 3u, the ODE we saw on the previous slide. Assume that we have two solutions, u and v, to this equation, and define w as above, where w is alpha u plus beta v, for any real numbers alpha and beta. From what we know about now we consider the derivative of w. This is equal to the derivative of alpha u plus beta v. That's how w is defined. From what we know about derivatives, this can be simplified to alpha times the derivative of u plus beta times the derivative of v. Since u or v are solutions of the differential equation, we know that their derivatives are equal to 3 times the function. So the derivative of u is equal to 3 times u, and the derivative of v is equal to 3 times v. This is what the ODE tells us about these functions. Now, factoring out the 3, we see that all of this is equal to 3 times alpha u plus beta v, which is the same as 3 times w. Putting this all together, we have shown that the derivative of w is equal to 3 times w, which says that w is a solution of this differential equation. An important note is that the idea of homogeneous is only applicable to linear differential equations. If the equation is nonlinear, this property does not hold. In general, we will only consider linear equations in this class, mostly because they are simpler and easier to understand. However, also, if you wish to consider nonlinear equations, you first must use the properties and tools that you develop for linear equations as building blocks.